So this video is going to look at polar covalent bonds. I want to talk a little bit about their definition, and then I'll give you the classic example of a molecule that is held together by polar covalent bonds, which is a water molecule. So with a polar covalent bond, what we've got is a situation where atoms are sharing electrons. So that's where the covalent part of this is coming from. However, they are not sharing those electrons equally. And so we're ending up with a situation where the molecule overall is polar. And what that means when we talk about polar from the standpoint of chemistry is the molecule has ends that are oppositely charged. So that's where the polar part of this is coming from. Now that we've kind of defined it, what I want to do is, again, give you that example showing you a water molecule. So a water molecule is, of course, H2O, right? And it's composed of 2 hydrogen atoms and a single oxygen atom. And I want to talk with this video a little bit about the structure of oxygen and about the structure of hydrogen as well, and why they want to come together to form these polar covalent bonds. So I have drawn out an atomic orbital model, a representation of what oxygen looks like. And you may remember that it has 8 protons that are located in the nucleus. So here's my little example of the nucleus, and to keep it simple, I just drew 8 plus, okay, meaning that we've got 8 positive charges there in the nucleus. And you may also remember from back when you learned atomic structure that all of these atoms that exist have, at least in their natural form when they're not ions, they have the same number of electrons and they have the same number of protons. So we've got 8 protons here in the nucleus. With oxygen, we've got 1, 2, 3, 4, 5, 6, 7, 8 electrons that are floating around in those atomic shells or orbital shells. Electrons are negatively charged, and because we've got 8 positively charged protons and we've got 8 negatively charged electrons, oxygen as a whole, as an atom, does not have a charge to it. But it does have a different problem. So if you guys remember from back when we learned about electron shells and how electrons are actually assigned to these electron shells or atomic orbitals, you learned that the innermost shell, right, that's the one that's closest to the nucleus of the atom, can hold a total of 2 electrons. And once it's got 2 electrons, it's full. You also learned that the shells after that, so the outer shells, which are known as valence shells, can hold 8 electrons. And they want to hold 8 electrons because when an atom has 8 electrons in that valence shell, that's what makes it most stable. So oxygen's problem is it does not have 8 electrons. It has 6. And so it's not as stable as it could be. If you look down here at hydrogen, of course, hydrogen has just a single proton. So I've drawn 1 plus in here. And because it has 1 proton, 1 positive charge, it also is going to have 1 electron or 1 negative charge. So here's that single little electron, and it's in its innermost shell. And remember that innermost shell, the one that's closest to the nucleus, it can hold a total of 2 electrons, and then it's full. Hydrogen's problem is it has, because it's got 1 proton, only a single electron in that shell. So it really needs another electron in its outermost shell, which in this case is the first one, right? In order to be full and to be as stable as it can be. So what we see happening when we have oxygen and we have hydrogen and they are all trying to make themselves more stable by filling up their shells is we get a chemical reaction. And if you look at what has actually happened over here, the oxygen and the hydrogen molecules have bound together. And by doing so, this hydrogen is sharing one of its electrons with the oxygen, and this hydrogen is sharing one of its electrons with the oxygen. And because they're sharing, in a way, we now have 1, 2, 3, 4, 5, 6, 7, 8 electrons in that valence shell, which is how we make it most stable. So oxygen is happy. But if you look at what's going on with hydrogen as well, before we talked about the hydrogens, they need 1 more electron and then they're going to be full, they're going to be stable, that's what they want. And if you look at what's going on here, we have each of these hydrogen atoms that are sharing one of oxygen's electrons, and that really is giving them each a full outermost shell because they've got 2 in the shell. Here's where the polar covalent bonding comes in. So over here, we have a bigger atom, right? Oxygen is quite a bit bigger. Hydrogen is quite a bit smaller. We talked about the fact that this is a covalent bond type, right? It's polar covalent, so they are sharing electrons, but they don't share them unequally, okay? And the reason for this in chemical terms is because oxygen is a little bit more electronegative. I'm a biologist, so here's how I tend to explain it, and your chemistry teacher may hate this, but I think of these atoms, right, in a tug of war. Oxygen and hydrogen are fighting over these electrons that they're sharing, and oxygen is bigger, so it has those electrons more. And because it has the electrons more, the electrons are over on this side of the molecule more, and they are over on this side of the molecule less. So what we have now is a situation where we've got a positive charge of 8 kind of on this side of the molecule coming from those 8 protons, but we've got negative charges, okay, that add up to 10 on this side because usually the electrons are over here, and that causes a partial negative charge on that side of the electron. So here's our little symbol that you'll see written in chemistry that indicates a partial negative charge, that we've got a polar molecule because it's negative on this side because we've got a higher density of electrons over here. Down here, we actually end up with a partial positive charge because we have these 2 positive charges, but most of the time the electrons are kind of over here, and every so often they get down here with the hydrogen, right? Shared but not shared equally. So we end up with a partial positive charge on the water molecule. Anytime you have a molecule, okay, that again, its 2 ends are opposite, so we've got a partial positive charge on one end, a partial negative charge on one end. That's when we have a polar covalent molecule, or a molecule that's held together with polar covalent bonds. So this video is going to build on what we learned about when we talked about polar covalent bonds to introduce you to hydrogen bonds. So hydrogen bonds form between polar molecules that, as the name implies, contain a hydrogen atom. A great example of this, one that you're already familiar with, is water, right? It's a polar molecule for reasons that we talked about in a previous video. And it contains hydrogen atoms, and so water molecules tend to have hydrogen bonds between them. One of the things that I want to say about hydrogen bonds that sets them apart from an ionic bond or a covalent bond or a polar covalent bond is that there is no exchanging, no sharing of electrons in this type of bond. What it is actually is a magnetic interaction that's happening again between these polar molecules. So we previously talked about water molecules and the fact that they've got this end, the oxygen end, which is a little bit more electron dense, and because of that it has a partial negative charge. And we've got this hydrogen end of the molecule that's a little bit more proton dense because it doesn't have the electrons equally, and so it's got a little bit of a partial charge to it. So we've got a polar molecule, it contains hydrogen, and it has this magnetic interaction with other water molecules. I want to draw this out for you and show you why. So let's imagine we've got a little drop of water, and I'm going to draw in several water molecules that are making up this little drop of water. Here we've got a water molecule with a positive end. This is the negative end of another water molecule. There is going to be a magnetic attraction between those 2 ends. So this water molecule and that water molecule are going to cling together just like the ends of a magnet would. Over here, again, we've got a positive end there and a negative end here. These water molecules, opposites attract, right, are going to want to cling together. This positive end is going to be attracted to that negative end, and so we're going to have all of these water molecules kind of cohesing down into the smallest possible space, and they're being held together literally just like magnets will kind of bind together and hold each other together. This is actually a property of water molecules, which is known as cohesion. So cohesion is the tendency of water molecules to kind of bind, attract, not really bind because they're not sharing or exchanging electrons, but attract to other water molecules and tend to kind of hold together in these little cohesive units. That's what's responsible for raindrops, right? So when rain falls from the sky, it falls in these little cohesive units that are being held together by the hydrogen bonds. It doesn't fall as individual, separate little water molecules that are coming down from the sky. So that's the property of cohesion that we see with water molecules because they're held together by hydrogen bonds. The other thing that you'll see, the other property that water has is what's known as adhesion. So you have probably seen, here's my terrible drawing of a blade of grass. A blade of grass. And if you get up in the morning, you may notice little dewdrops, right, on the blades of grass. And the reason for that is because water is polar, because it has these oppositely charged ends, it tends to cling to anything else that is also polar. So there must be some polar chemical, something that's polar in blades of grass that's going to cause these little drops of dew to actually attach to the grass blades. And this is a property of water that's known as adhesion. So it tends to stick to things also that aren't water because of the fact that it has this little magnetic ends, basically. I want to give you an example of adhesion and cohesion that's important to the human body. So what I've drawn here are little microscopic structures that are actually in your lungs. These are known as alveoli. They're also sometimes just referred to as air sacs, but when you inhale oxygen, eventually where that oxygen ends up is in these little tiny air sacs. And that's where the gas exchange happens, where the oxygen moves into the blood, where the carbon dioxide moves out of the blood into the alveoli, so that when you exhale, you're releasing that carbon dioxide. The lungs are a really humid environment, so there's lots of water there. They're basically at 100% humidity. So as you look at one of these alveoli, I'm using this one just as an example here, because they're so humid, because there's a lot of fluid in them, there's lots of water molecules. And remember that water has this property of adhesion, where it tends to adhere to things. And so if you look at the wall of this alveolus, this little single air sac here where we need oxygen exchange occurring, we've got water molecules that are attaching themselves to the wall. But the other thing, because water molecules have that cohesive property, is that these water molecules, the positive end of one is attracting the negative end of an adjacent one, and these alveoli are microscopic structures, so these water molecules are really in much more close proximity than they look in this diagram. But because there's this fluid that's present, this water that's present, the water's polar, it has that property of cohesiveness, of magnetic attraction, and it has the property where it adheres to the wall of the alveoli. What would happen if it weren't for a chemical in our lungs that protects us is the positive end of this molecule would attract the negative end of that molecule. This molecule is adhered to the wall, this molecule is adhered to the wall, and when they attracted each other and came together, they would actually pull the wall out of the alveolus shut. So our bodies produce a chemical. This chemical is known as surfactant, and basically what surfactant does is it gets down in there and it interacts with these water molecules, and I don't want to say creates a shield, but that's probably the simplest explanation. It kind of shields them and prevents them with being able to interact with each other so that they can't collapse those air sacs down. Many of you are probably familiar with a condition that can affect premature babies. So usually this surfactant isn't produced in any great amounts until about 35 weeks in utero. For babies that are born at 35 weeks or below, or even sometimes if they're full term, they have lungs that aren't fully developed. And what that means basically is they're not producing this surfactant. So before we knew what the problem was, and this was relatively recently, even in the 60s, what used to happen was these babies were born, their lungs weren't developed, they didn't produce the surfactant, and so all of these millions of air sacs within their lungs would collapse because of these cohesive forces and these adhesive forces that are working between the water molecules in the lungs. And most of these babies that were born with this situation would struggle to survive and usually didn't live more than a few days. And it would be very hard for them to inflate their lungs. And actually, as they tried to open up those air sacs, because that magnetic attraction between water and molecules was so strong, they would end up tearing this really delicate tissue that's in the lungs. What we do now, if we know a baby's going to be born prematurely, is the mom will get a steroid injection. That's to help the lungs to develop, which means we're going to get them to start producing that surfactant. And if that isn't enough, then there are also surfactants that are produced that can be put into the baby's lungs to prevent this from happening so that we don't lose babies anymore due to those interactions that are happening between water molecules in the lungs.